Integral representation of beta function. I just realized today that till now, like, I haven't really done this thing, the integral representation of beta function on my channel. Though I have already covered the other integral representation of, let's say, zeta of s, which is 1 by gamma of s, integral from 0 to infinity t to the power s minus 1, sorry, t to the power s minus 1 by e to the power t minus 1. I've already covered this one, or if we make here plus, this is just eta of s. Yeah, we have covered those things, but not for this one. So let's do it today. So first of all, we write in terms of its summation notation, in terms of the sum. Yeah, and that will basically be sum from n equals to 0 to infinity, and then there's alternating minus sign, and there are odd terms in denominator, so 2n plus 1. So I think you can get this, yeah, odd terms and alternating minus sign. Now, how do we take it to integral form? Now, we will basically try to take the inverse Laplace transform of this function, which is comparatively easier. So basically, if we just take 1 by gamma of s, multiply by 1 by gamma of s, and also multiply by uh, gamma of s here. Okay, minus 1 by, and then 2n plus 1 to the power s. Now notice that this is just a kind of Laplace transform, you know, like basically if you take the integral from 0 to infinity, if there's e to the power minus of 2n plus 1 s, sorry, not s, t, and then t to the power s minus 1. If this is the case, then the integral will just be, we will use the formula of Laplace transform, so this will just be gamma of s by 2n plus 1 to the power s. Yeah, so using this we can basically get the expression. So let's try to introduce the integral. We have 1 by gamma of s, sum from n equals to 0 to infinity. This is kind of greater than equals to, okay, integral from 0 to infinity, and then minus 1 to the power n, integral from 0 to infinity e to the power minus 2n plus 1 t to the power s minus 1 dt. Okay, now after this let's try to take the negative sign inside. Yeah, and then let's try to use the sum and integral. Yeah, so 1 by gamma of s, integral from 0 to infinity. Yeah, and then here's a sum from n equals to 0 to infinity, and then let's write this as e to the power minus t. Yeah, and then minus of e to the power minus 2. Yeah, minus of e to the power minus 2 to the power n. Yeah, and then t to the power s minus 1. I'm doing this because now this becomes a geometric sum, isn't it? And that will be helpful for us. So 1 by gamma of s, isn't it? Okay, and also here's a t as well. I forgot that. Okay, so now these two are just constant, and now this is just to be the sum. Yeah, and the integral from 0 to infinity, we have e to the power minus t to the power s minus 1, and if you sum this, the first term is just 1 by, and note that the modulus of this thing is less than 1, so 1 by a minus r, a minus our r is basically minus e to the power minus 2t. Note that, please note this thing, because, and this is going to the power of n, yeah, in the geometric sum. So 1 minus e to the power minus 2. Yeah, this is our sum, and then there's a dt. So now we have 1 by gamma of s, integral from 0 to infinity, e to the power minus t to the power s minus 1 by 1 plus e to the power minus 2t dt. Okay. So now if we multiply numerator and denominator by e to the power t, what do we get? 1 by gamma of s integral from 0 to infinity t to the power s minus 1 by e to the power t plus e to the power minus t dt. And this is the required integral representation for the beta function. Yeah. So let us write this over here, and this is 1 by gamma of s integral from 0 to infinity t to the power s minus 1 by e to the power t plus e to the power minus t dt. Fine. Now, very nice. And talk about the flow. We first change it to its sum representation, and notice that here we could have applied inverse Laplace transform, and using that we got our integral representation. Extend the sum and integral, and there was geometric sum which we evaluated, and then we got the answer. So this was it. This was a pretty easy thing, but I just wanted to make a complete channel, so that's why I just did this. Hope you enjoyed the video. Thanks for watching, and look forward to seeing the upcoming videos too.